Everything that has ever fallen into a black hole is gone. That's what you were told. That's what physics said for 50 years. That's what the most famous scientist alive repeated in lectures, in papers, in interviews, everywhere. They lied. Information doesn't die, it survives. But where it goes, and what that means for everything you think is real, is worse than the lie. Things vanish around us all the time. Snow melts, a flashlight fades in the dark, chalk gets wiped off a board, buildings are demolished. To us, it feels simple. Something was there, and now it's gone, permanently. If something is wiped off a chalkboard, there's no way to know what was written there anymore. That just seems obvious. It doesn't. To physics, the obvious answer is almost the exact opposite. Take a shattered cup. In principle, it could be reassembled, even if it broke into 1,000,000 pieces, because the information about the cup's original form never truly disappears. It only spreads out into the world, into cracks in the ceramic, into the motion of the fragments, into the heat released by the impact, into the sound wave moving through the air. Physically, every atom, every bit of momentum is still there. The information has simply been redistributed. We call that disappearance. Physics calls it loss of access. And those are not the same thing. The gap between them is enormous. Quantum mechanics stands on one side of that gap and draws a hard line. The trace must remain. Information cannot be destroyed, ever. And this applies to everything. If quantum mechanics is right, then the universe does not merely experience events. It preserves their imprint in its physical state. Every particle collision, every beam of light, every city that vanished, every person who ever lived. Not in the form of some hidden record you could simply open and read, but in the physical state of reality itself. Information about the past can become inaccessible, unreadable, practically lost. But if it can truly disappear, then maybe true oblivion is possible. Not just forgetting, not just destruction, but an ending without a trace, without recovery. Physics doesn't treat the past as something that can simply fall out of reality. Every event leaves a physical imprint. Every collision, every motion, every vanished thing remains folded into the state of the world. Even when the trace is unreadable, it's still there. That's the rule. A black hole breaks it. This is where the black hole becomes the problem. It doesn't merely destroy things. It takes them somewhere nothing can return from by definition. Consider this. The universe must somehow preserve the difference between a star that fell into a black hole and the British Library falling into the exact same one. The universe must remember what exactly went in. But Hawking's calculations struck directly at that idea. The radiation coming from a black hole says nothing about what previously fell into it. Two black holes that look identical from the outside radiate in exactly the same way. It doesn't matter what each one consumed beforehand. A black hole does not merely hide information, it seems to erase it, as if the universe does not remember after all. But the implications were too severe to simply accept. If information can truly disappear, then it's not just some isolated theory about black holes that breaks down. One of the deepest principles of quantum mechanics collapses along with it. So physicists began searching for a way out, and the first possibility seemed almost obvious. Maybe the problem is simply that we're looking too early, before the black hole has a chance to return what it took. After all, a black hole loses mass gradually, becoming smaller and smaller. Maybe the information stays inside this whole time, and only at the very end of its life does the black hole release everything back into the universe in one final burst. At first glance, this looks like a rescue. The information has not been destroyed. It has simply been waiting inside until the last possible moment. But this solution falls apart almost before we can finish formulating it. Near its end, the black hole should already be tiny, smaller than an atom. And yet, the amount of information it would need to return remains enormous. If it once swallowed entire stars, then the full history of everything that fell in would somehow have to come back out of an object that is itself almost gone. It does not solve the paradox, it inherits it. The first simple solution does not save the information, it only postpones the paradox, pushes it to the very end of the black hole's life cycle. But the failure of this idea did not mean physicists had run out of hypotheses. Quite the opposite. Very quickly, an entire family of solutions emerged around one central idea. Maybe a black hole never fully evaporates at all. Maybe, at the final stage, Hawking radiation simply stops, leaving behind a tiny stable remnant. The idea seemed serious enough that physicists began developing it not as philosophical speculation, but as a full-fledged theory. Such a remnant would be Planck-sized, around 25 orders of magnitude smaller than an atom. An object so small that it barely interacts with the outside world at all, where our ordinary understanding of space and matter already begins to break down. And yet, somehow, it would still contain information about everything that had ever fallen into the black hole. At first glance, this looked far cleaner, despite its absurdly tiny size. The information no longer had to be thrown back into the universe in one impossible instant, and that had been the core problem all along. The new solution seemed genuinely elegant. The information remains trapped inside the remnant forever, inaccessible, but not destroyed. But along with that elegance came a new price. We were still talking about a microscopic object that somehow had to store information about everything a black hole had consumed over billions of years. For a remnant to truly store the information of an arbitrarily large black hole, it would need an almost infinite number of internal states, while keeping nearly the same mass and size. And that very quickly begins to break quantum field theory. Objects like this should form far too easily. The vacuum should literally boil with the creation of these objects. The universe would be flooded with black hole remnants. But we do not observe that. And once again, the paradox refuses to disappear. It simply changes shape. First, the final explosion did not work. Now the eternal remnant doesn't work either. Information can neither be returned nor hidden away forever. The simple solutions were gone. From this point on, physicists were no longer arguing about the details of black holes, but about which law of nature they were willing to sacrifice. And that was the beginning of one of the most epic scientific debates of the modern era. On one side was Stephen Hawking, the man who had discovered that black holes should radiate and slowly evaporate. and his calculations led to an uncomfortable conclusion. When a black hole disappears, the information about what fell inside disappears with it. Hawking was willing to accept this, and he did. And he did not back down. He repeated the conclusion in lectures, in papers, in interviews. Information is destroyed. The equations say so, full stop. For him, a black hole really could be a place where the universe loses its memory. But to other physicists, this didn't sound like a quirk. It sounded like a catastrophe. If information disappears, quantum mechanics stops being reversible. Knowing the final state of a system would no longer let you reconstruct its initial state. The past does not merely become inaccessible, it's cut out of the mathematical description of the world. And this breaks not a metaphor, but the actual bookkeeping of quantum theory. In ordinary quantum mechanics, the sum of all possible outcomes must add up to 100%. Everything that can happen has to be accounted for somewhere. If information falls into a black hole and vanishes forever, that sum simply does not add up. One of the people who could not accept this was Leonard Susskind, a physicist horrified by the implications of Hawking's result. For Susskind, the question was brutal. If information inside a black hole is truly erased, then all of quantum mechanics is just a house of cards. To him, that was too much to give up. If saving black holes meant abandoning the conservation of information, then we were breaking one of the most reliable parts of physics. And for what? Mind you, at the time, black holes existed for science only on paper. No one had observed them yet. Hawking, meanwhile, would state it bluntly in his lectures. Information is lost, accept it. And that's how the conflict began, what Susskind himself would later call the Black Hole War. For decades, Hawking, Susskind, and other major physicists tried to understand what would ultimately survive: Hawking's evaporating black hole or quantum mechanics. Susskind would later write a book about it. For him, this was not a dispute over details. It was a fight for a principle without which quantum theory loses reversibility, and with it, the link between past and future. In 1997, the dispute reached a climax and even took on an almost theatrical form. Hawking and Kip Thorne made a bet with John Preskill. Hawking and Thorne bet that information really is lost in black holes. Preskill bet that some kind of escape from this dead end had to exist. The wager was symbolic, but almost too perfect. An encyclopedia, a book packed with information, became the prize in an argument over whether information can disappear from the universe. By then, the debate had already been going on for more than 20 years. And then, in 2004, at a conference in Dublin, something happened that almost no one expected. Hawking suddenly conceded defeat. But even that, he did in his own style. He didn't simply walk on stage and say, "I was wrong." He presented a new calculation and argued that information probably does not disappear in a black hole after all. But not because it later flies back out in the ordinary sense. Rather, because a true event horizon may never form in quite the same way physicists had previously assumed. Then he paid his side of the bet. He gave John Preskill a baseball encyclopedia. For a moment, it may have seemed as if the war was over. But Hawking had only conceded the overarching principle. The black hole itself did not get any less mysterious. His new calculation never became the accepted solution to the paradox, and it didn't explain exactly how the old picture of a black hole was supposed to be replaced. So the main question did not disappear. It only became sharper. Where the hell does a black hole hide the information while it evaporates? After Hawking's concession, it may have seemed that Susskind had won. Information is not destroyed. Quantum mechanics survives, which means that somewhere in the picture of a black hole, there must be a missing piece. And Susskind proposed one of the most elegant. It was called black hole complementarity. The idea sounds like a sleight of hand, but behind it was serious physics. Maybe there is no contradiction at all, because different observers simply described the same situation in different ways. Imagine an object carrying information falling into a black hole. For the falling object itself, everything looks normal. It crosses the event horizon and continues falling inward. In its own description, the information has gone beyond the horizon. But an outside observer sees a different picture. To them, the object never crosses the horizon in the ordinary sense. It seems to slow down right at the edge, redden, fade, smear across the horizon, and the information it carries becomes encoded on the outside. And later, very slowly, that information may come back out with Hawking radiation. At first glance, this looks like impossible duplication, one copy of the information inside, another outside. But complementarity says no. There are not two copies you can place side by side and compare. They are two different descriptions of the same physics. The falling observer cannot get back out and report what they saw inside. The outside observer cannot look beyond the horizon and check the internal version. No one sees both pictures at the same time. And as long as that remains true, the paradox seems to disappear. Information is not destroyed, but quantum mechanics also does not forbid this double description, because no observer can catch two copies in a single experiment. It was a beautiful solution. So beautiful that for a while it really looked like a way out. Physicists who had spent years fighting the paradox could finally breathe. Information is not destroyed, and it is not hidden in an impossible remnant. It is simply described differently depending on where the observer stands. Quantum mechanics survives, general relativity survives, nothing has to be sacrificed. But this idea had one weak point. Everything depended on the condition that no observer could ever check both versions at once. And in 2012, 4 physicists decided to test exactly that condition. Ahmed Almhiri, Donald Marolf, Joseph Polchinski, and James Sully, later known simply by the first letters of their surnames, AMPS, they built a thought experiment. Imagine a very old black hole, one that's already emitted a lot of Hawking radiation. An outside observer collects this early radiation and extracts information from it. Then that observer jumps into the black hole. If complementarity is right, they should not see anything that would allow them to compare the outside and inside versions. But the AMPS calculations exposed a structural problem. Complementarity works only if 3 conditions hold at once. Hawking radiation must preserve quantum information, rather than turning it into random thermal noise. Physics at the horizon must remain unremarkable. No exotic effects right at the horizon. And a falling observer must notice nothing special when crossing the horizon. Each of these conditions seemed reasonable on its own. AMPs showed that all three together are incompatible. In principle, an observer could collect enough early radiation, then cross the horizon and check what happens to the same information inside. Which means you can no longer simply compartmentalize the two versions between different observers. But complementarity depended precisely on that experiment being impossible. The maths said, no, it's not impossible. And when this beautiful solution began to collapse, an even harsher idea emerged from the wreckage. If information really does not come back out, then the event horizon may be nothing like the calm place Einstein imagined. To put it mildly, suppose, for a moment, that the information really does come out. Quantum mechanics is saved, Susskind was right, we can breathe. But then the question becomes, how exactly does it come out? A black hole does not evaporate instantly. It loses mass gradually, emitting Hawking radiation over an enormous span of time. Some of that radiation escapes earlier, some escapes later. And here's the problem. For all of that radiation to ultimately contain information, rather than just random noise, the early and late portions of the radiation must be entangled with each other. But quantum entanglement has one strict rule: the monogamy of entanglement. A single quantum system cannot be fully entangled with two independent systems at the same time. Think of it like a key and a lock. If the key matches one lock, it cannot also match another at the same time. And the late radiation is already entangled with the interior of the black hole, and that connection is not incidental. The quantum fields near the horizon are in a special state. Their fluctuations on the two sides of the boundary precisely cancel each other out. That's what makes the horizon a calm place. A falling observer passes through it and sees exactly what they would see in ordinary empty space. Nothing special. But if that same late radiation also has to be entangled with the early radiation, so that information can come out, then its old entanglement with the interior can no longer remain intact. And if that old entanglement is broken, the balanced state collapses. In place of a quiet boundary, something else appears. A high-energy excitation of the field, a flood of ultra-energetic quanta. This is what remains when the special quantum equilibrium at the horizon is destroyed. That's how physics arrived at the idea of a firewall at the edge of a black hole. The event horizon may turn out to be a devastating barrier, burning up anything that tries to pass through it. Either the entanglement with the interior remains and information is trapped, breaking quantum mechanics all over again, or the information escapes and the horizon is no longer calm. There's no middle ground. General relativity says the horizon is smooth, and a falling observer feels nothing. Quantum mechanics says that if information survives, a wall stands at the horizon that will incinerate any falling observer. Both theories have been tested with a precision almost any other science could envy, both work everywhere we've tested them, and here they demand the exact opposite. Physics had once again reached a dead end with no visible way out, and it was at this moment that the man who had started all of this returned to the story: Stephen Hawking. In 2016, just 2 years before his death, Hawking published a new paper with Malcolm Perry and Andrew Strominger. And in a way, the story came full circle. The man who'd created the black hole information paradox in 1974 and who had spent decades insisting that information could be lost forever was now, near the end of his own life, trying once again to find a way to save it. After the Firewall, the idea sounded almost unbelievably modest. Maybe black holes are not completely bald, as physicists had once thought. Maybe everything that crosses the event horizon leaves behind a faint quantum imprint on its surface. Soft hair. Of course, this is not hair in any ordinary sense. Hawking, Perry, and Strominger were referring to very low-energy quantum excitations, soft photons and soft gravitons, that may remain imprinted at the boundary of a black hole. Each falling particle slightly changes the quantum state of the horizon, leaving behind an almost imperceptible trace. And if so, information does not disappear completely. It remains on the surface of the black hole as an infinitely delicate structure of quantum imprints, too weak to be seen classically, but perhaps enough to keep the universe from losing its memory of what fell inside. It was a beautiful idea, and at the same time, a deeply human one. After decades of arguments, Hawking had returned to the same question he himself had once forced physics to confront. Can the universe truly forget anything? But the work remained unfinished. The calculations suggested that soft hair might simply not be enough. There may not be enough of these quantum traces to preserve all the information in a large black hole. In 2018, Hawking died. He never lived to see the end of the story of a paradox of his own making. Physics had long needed a way to test what should actually happen to information if a black hole evaporates completely. Not through conceptual hand-waving like, "It's hidden on the horizon," or "It comes out with the radiation," but as a concrete calculation. The test was proposed back in 1993 by Don Page, a physicist who had once been Hawking's student. He asked a question that was simple in form. If a black hole gradually evaporates, how should the entanglement of its radiation change? If information is truly lost, the picture looks bleak. The black hole emits more and more radiation, and that radiation becomes more and more entangled with what remains inside, and the entropy keeps rising. The longer the black hole lives, the more disorder it leaves behind. But if information is preserved, the graph should behave differently. At first, the radiation really does look increasingly chaotic. Information seems to sink deeper and deeper into the noise, but at some point, roughly halfway through the black hole's lifetime, the curve must turn around. New radiation no longer increases the disorder. Instead, it gradually begins to reveal hidden connections with what came out earlier. By the end of evaporation, the entropy should fall back to zero. In other words, the entire history of the black hole should resolve back into a pure quantum state. The information did not disappear. It was monstrously scrambled, but not destroyed. This graph became known as the page curve, and for decades it remained an almost perfect test that physicists could not pass. Everyone understood if a theory of black holes ever produced the correct page curve, it would be a powerful sign that information survives after all. But in Hawking's standard calculations, the curve did not turn around. The radiation continued to look like thermal noise. Then, in 2019, the calculations finally produced the result physicists had been looking for. Ahmed Almhiri, Netta Engelhardt, Jeff Pennington, Henry Maxfield, and other physicists independently arrived at a new picture. If the entropy of a black hole is calculated in a more nuanced way, taking gravity and quantum entanglement into account, the page curve really does turn around. For the first time, the mathematics began to say what physicists had been trying to prove for decades. Information survives. For a moment, it looked like an answer. But, as always in this story, the answer turned out to be worse than the question. To make the page curve turn around, the maths forced a bizarre concession. Regions inside the black hole that, from the point of view of entropy, began to belong to the radiation outside. They were called islands. They are inside the black hole, but in the correct calculation of information, they have to be counted as part of the outside system. In other words, the mathematics said information survives. But for that to happen, the inner region of the black hole can no longer be a completely separate inside. The inside begins to bleed into the outside. And this is where the paradox, for the first time, stops being merely a question about black holes. It begins to turn into a question about what it even means to be inside space. The islands answered the question of information, but along with that answer, they brought something else. A hint that something is wrong with space itself inside a black hole. We're used to thinking about a black hole like this. Outside, there is the event horizon. Inside, there is a vast three-dimensional bulk where everything falls. It seems obvious. If information is stored somewhere, it's stored there, inside, in the bulk. There's simply nowhere else for it to be. But black holes had been hinting for a long time that this obvious picture was not so obvious after all. Back in 1972, Jacob Bekenstein asked a simple question. How much information can a black hole contain? The answer was strange. That amount doesn't grow with volume. It grows with the area of the event horizon. This is worth pausing on for a moment. Imagine a city. Everything that happens in it exists inside it. When new districts are built, when new streets and neighborhoods appear, the city limits expand, and everything new fits into the growing space. The information about the city lives in the city, inside it. This feels so obvious that it almost seems strange to say out loud. But Bekenstein's calculations suggested that the information capacity of a black hole does not depend on the volume inside. It's determined by the area of the surface outside. As if everything that happens in a city were determined not by what is inside it, but by the length of the fence around it. Physics behaved as if the three-dimensional interior of a black hole were not the real storage space. As if everything that happens inside a black hole is somehow already written on its two-dimensional boundary, and in a sense remains there. Physicists called this the holographic principle. In the 1990s, the idea was stated explicitly. Everything that happens inside a region of space can, in principle, be encoded on its boundary. And in 1997, Juan Maldacena gave this idea a concrete mathematical form. His work showed that a theory of gravity in the bulk can be mathematically equivalent to a quantum theory on its boundary, without gravity. An entire dimension turned out to be redundant. The entire physics of the bulk was mapped onto the boundary without losing a single shred of information. It became the most cited paper in the history of theoretical physics. And it wasn't only beautiful, it worked. Problems that were impossible to solve in the bulk could be solved on the boundary. The two descriptions gave the same answers. The bulk and the boundary turned out to be two languages for the same physics. And now, the islands were pointing in exactly the same direction. Regions inside the black hole that, in the correct entropy calculations, turn out to be part of the radiation outside. These are not a mathematical trick. This is holography in action. The interior doesn't disappear, but it stops being independent of what is outside. It begins to look like a projection, something that can be reconstructed from information on the surface. Again, a black hole is not just an object with a horizon and mysterious depths. Its three-dimensional inside may be only a shadow of what is written on a two-dimensional boundary. And then the answer to the question, where does the information go, sounds almost frightening. It may not go anywhere deeper inside. Maybe that was the wrong picture from the very beginning. The information was not hiding in the interior. The mathematics suggests it had been written on the boundary all along, and what seemed like the interior was only the way that boundary, in a certain sense, looks from the inside. But black holes are not exceptions to physics. They obey the same laws as everything else in the universe. And if their three-dimensional interior is a projection of a two-dimensional boundary, then one question arises. Is this unique to black holes? Because here's the thing. A black hole obeys the same laws of physics as everything else. It's an extreme object, but not a miracle. And if somewhere a three-dimensional inside can be encoded onto a two-dimensional surface, then that principle can no longer be contained within the black hole. It points outward, at the space around us, at the entire observable universe. If the contents of a black hole are encoded on its event horizon, then what is our universe encoded on?